Alright, welcome to lesson 8 of module 1. Today we're going to be comparing numbers that are written in scientific notation. First we'll review how to write numbers in scientific notation, and then we'll go through the process of what it means to compare them, how we do that with a ratio, and through applying our knowledge of exponent rules. So let's go ahead and get started. Alright, just to review some background information, we write numbers that are really big and really small in scientific notation because it makes them easier to work with, and you'll see that today when we work with these really large and really small numbers. So say I have the number 58302. If I wanted to write that in scientific notation, I would identify where do I want to put my decimal, where do I want my leading digit to be. So I want this to be my leading digit, and I want my decimal to go here. Right now my decimal is here, so I need to move my decimal 1, 2, 3, 4 spaces. Okay. And so my final number will be 5.8302 times 10 to the 4th. Because if I were to multiply this out, it would equal this number that I started with. Okay? Because I would just move that decimal point 4 places. You can also do it with really small numbers. If I have 0.01204, I would identify my leading digit. Well, I want this to be my first digit here. So I'm going to be moving my decimal point right here. I'm going to be moving it back 2 spaces. So this is the same as 1.204 times 10 to the negative second. And it's negative because I'm moving it back 2 spaces. Okay? And if I were to actually multiply this out, this is the number it would come out to. Okay? Let's go ahead and get into our new learning today, where we are going to be comparing numbers by writing them like this. Okay? Alright, beginning with exercise 1, it says the Federal Reserve states that the average household in January of 2013 had $7,122 in credit card debt. About how many times greater is the U.S. national debt, which is $16,755,133,009,522. Rewrite each number to the nearest power of 10 and then compare them. So the first thing we want to do is we want to take these numbers and we want to round them off, okay, to the nearest power of 10. So this first one, $7,122, the nearest power of 10, so we have 10, 100, 1,000, 10,000. Those are powers of 10, right? So the nearest power of 10 here is probably 10,000. And then the second number, 16, it's very long, 755133009. 522. We want to round this off to the nearest power of 10 as well. So again, this number is what? 16 trillion. So we're either going to round down to 10 trillion or up to 100 trillion. And in this case, I rounded up my first number, so I'm going to round up this number as well, just so it's a little bit more accurate. So this is going to be 100 trillion, the number that I'm writing. So we have 100, that's in the trillions. Then we have 3 zeros to represent billions, 3 zeros to represent millions, 3 zeros to represent thousands, and 3 zeros to represent our ones. Okay? Now that we've written them in powers of 10, we're going to write them in scientific notation. So this number, I want to write that in scientific notation. So the first thing I'm going to do, here's my leading digit. I want the decimal point to go right here. So I'm going to be moving it 1, 2, 3, 4 spaces. So this first number is going to be 1 times 10 to the 4th. Or we don't really need this 1 because that doesn't do anything. 1 times 10 to the 4th is the same as 10 to the 4th. Okay? The second number, I'm going to do the same thing, rewriting this in scientific notation. I want my decimal here. I'm moving it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 spaces. So this is the same as 1 times 10 to the 14th. Again, I don't need my 1 times because it's just the number 1. So I'm I'm just going to write it as 10 to the 14th power. So now I've estimated these as powers of 10, and I want to compare them. I want to see, well, how many times greater is this than this? So if we were ever trying to figure out how many times greater something is, we use division. So if I say how many times greater is 4 than 2, well, 4 divided by 2 is 2. So how many times greater is 10 to the 14th than 10 to the 4th? Well, I'm going to do 10 to the 14th divided by 10 to the 4th and see how many times greater it is. Well, one thing you should know working with exponents is that if we're dividing exponents to have the same base, right, all we have to do to these exponents is subtract them. So 10 to the 14th divided by 10 to the 4th is the same as 10 to the 10th power, right? 14 minus 4 equals 10. So the U.S. national debt is 10 to the 14th times greater, well, about, because we rounded, than the average single household, or the average household debt. Okay, make sure you have this down, and if it's confusing, that's all right. We're going to get a lot more practice in before you're released to do some of this stuff on your own. Okay, let's continue. All right, here's our new learning for today. We can compare very large and very small numbers by, first we write them in scientific notation, okay? Then we compare them as a ratio. Remember, a ratio is just a fraction. And then we simplify our numbers using our knowledge of exponents. If we're dividing and we have the same base, we would subtract those bases to get our final answer. For example, if I have, let's see, if I have 7 times 10 to the 3rd divided by 2 times 10 to the 2nd, well, I can divide 7 and 2. This becomes 3.5. And I can divide these because these are the same base. 3 take away 2 is 1. And that's what we're going to be doing today. Let's move on to some more practice. All right, exercise 2. It says there are about 3 million students attending school, kindergarten through grade 12 in New York. Express the number of students as a single-digit integer times a power of 10. So basically it's saying write it in scientific notation. So we have 3 million, so I know I'm starting with a 3. 3.0, you could just do 3. And we're doing times 10 to the, well, I'm going back, 1, 2, 3, 4, 5, 6. 10 to the 6th. Okay, again, this is the same as writing 3 times 10 to the 6th. Okay, and then goes on to say the average number of students attending middle school is 8 times 10 to the 2nd. So they've already given us a number in scientific notation. They said, okay, well, of all of these total students, these are the ones that are in middle school, 8 times 10 to the 2. How many times greater is the overall number of K-12 students compared to the number of middle school students? So this is what we're comparing. Overall to middle school. So this is how we're going to write our ratio. Overall number of students to middle school students. Okay. Well, the overall number of students was this number right here. 3 times 10 to the 6th power. And we're comparing that to the number of middle school students, which is right here. 8 times 10 to the 2nd power. Okay. So the first thing we are going to do is we are going to divide 3 and 8, and then we're going to divide our powers of 10. So in your calculator, or in my calculator, 3 divided by 8. Come up with a decimal that you get when you do that. You should get 0.375. Okay, so we did this, and this is what we got. Now we're going to do 10 to the 6th divided by 10 to the 2nd. Well, same base, so we subtract exponents. 6 minus 2 is 4. All right, from here we want to take this and actually write out the real number. So we're not leaving it in scientific notation. We're going to put it as our real number. So we're doing this decimal 0.375 times 10 to the 4th. That means I'm going to be moving this 1, 2, 3, 4 spaces to write it as an actual number. So that would be filled up with a 0 forever doing that. So the real number here is 3750. Okay? And just to answer the question, times greater. Again, my last step here was just turning this back into a regular number, not leaving it in scientific notation format. Okay? Let me know if you have any questions before we move to the next part of this. All right, exercise 3. A conservative estimate of the number of stars in the universe is 6 times 10 to the 22nd power. The average human can see about 3,000 stars at night with his naked eye. About how many times more stars are there in the universe compared to the stars a human can actually see? So we're going to be doing stars in the universe compared to the number of stars a human can actually see. Okay? So we're comparing the universe to the human eye. Okay? So the first number they give me is this number of stars in the universe, and they already have it written in scientific notation. 6 times 10 to the 22nd. The second number they give me is 3,000. I need to write that in scientific notation. So I'm going to do that here. 3,000. My decimal is right here. I want to move it to be right here. So moving it 1, 2, 3. So this is same as 3 times 10 to the 3rd. So I'm going to write that here. And then I am dividing these numbers. First, I'm going to divide my whole numbers. 6 divided by 3. This is 2. Then I'm going to divide my powers of 10. 22 take away 3. Well, 21, 20, 19. Now we could rewrite this out as 2 with 19 zeros that follow it to turn it out of scientific notation, but it doesn't actually tell me to do that, so I'm going to leave it in scientific notation because this is already written correctly, right? The decimal point is right here, the leading digit is correct, the scientific notation, we figured out the exponents, so it is about 2 times 10 to the 19 times more. Okay, make sure you have that down before we move on to exercise 4. Exercise 4, it says the estimated world population in 2011 was 7 times 10 to the 9th power. Of the total population, so out of that, 682 million were left-handed. Approximately what percentage of the world population, this one's going to be hard because we got to find a percent, is left-handed according to the 2011 estimation. So we're finding the percent of left-handed people in the world. So we're doing left-handed out of the total number of people. And we're going to get a number, and then we'll eventually turn that number into a percent. So the first thing I want you to do is fill in the numbers that go in this ratio. Write that number on top, the number of left-handed people, and then on the bottom, write the number of the total number of people in 2011. And what I want you to do is I want you to write both of these numbers in scientific notation. One of them is already given to you in scientific notation, the other is not. So take a minute to do that. Alright, so you should see that the total number of people is this one. So I'm literally just going to copy that down here. 7 times 10 to the 9th. And then we have 682 million. that are left-handed. So I'm going to write that number out, 682 million. And now I'm going to write it in scientific notation. Well, I want my 6 to be my leading digit, so I want it to say 6.82. And this is being moved 1, 2, 3, 4, 5, 6, 7, 8. So this is times 10 to the 8th. Okay, check that with what I got, and please make sure that you have it done correctly. All right. Now, one thing I want us to notice about this is that it says approximately. So we don't need to be completely like accurate here. So what I'm going to do is, I know that 6.82 is very close to the number 7. And if I have two 7s, then it's going to be a lot easier. So this is essentially very close to 7 times 10 to the 8th power. And then this is 7 times 10 to the 9th power. Okay. So from here, we're going to divide our numbers. So what I want you to do, what is 7 divided by 7? Well, 7 divided by 7 is 1. What is 10 to the 8th divided by 10 to the 9th? Well, 8 take away 9, -1. So this is our answer, but we want to write this as a percentage. So the first thing we need to do is write this as a fraction. Well, remembering our rules with negative exponents, if we want to turn that to a positive exponent, all we have to do is flip this over. So remember, we can disregard 1 times because this is not going to change anything. We just have 10 to the negative first. So I'm going to rewrite this as positive number. This becomes 1 over 10 to the first power. Okay? And then I'm going to solve. What does this actually equal? Well, 1 stays the same. 10 to the first power. 10 times itself 1 time. That's just 10. So 1/10. And from there, I'm going to turn this into a percentage. Well, 1 out of 10, this is the same as 10%. Right? And the reason I know that, if I were to add a 0 to both the top and the bottom, this is 10 out of 100, or 10%. So, how much of the population was left-handed in 2011? About, because we approximated, 10%. Okay. Let me know if you have any questions here before we move on. All right. The average person takes about 30,000 breaths per day. Express this number as a single-digit integer in terms of powers of 10. Let's go ahead and rewrite that number in scientific notation. I'll give you about 30 seconds. This number becomes 3 times 10 to the, we're moving this 1, 2, 3, 4 times. Okay, hopefully you got that correct. If the average American lives about 80 years, or about 30,000 days, how many total breaths will a person take in her lifetime? So now we have this number. So this is 1 day, right? We're trying to figure out how many times they're going to do that in 30,000 days. So we're going to be multiplying these two together. But instead of just multiplying these really big numbers straight up on our calculator, we're going to multiply them in scientific notation. So now I'm going to rewrite this second number in scientific notation. This is 3 times 10 to the 1, 2, 3, 4. Okay. So essentially we're going to be doing 3 times 10 to the 4 times 3 times 10 to the 4. All right. Now, we don't really need these parentheses, and we can multiply in whatever order we want. I'm going to multiply my numbers, my whole numbers together first. 3 times 3 is 9. Then I'm going to multiply my exponents. 10 to the fourth times 10 to the fourth. Well, if I have the same base and I'm multiplying these numbers, all I have to do is add my exponents. So this is the same as 10 to the, what's 4 plus 4? 8. So 9 times 10 to the 8th is my answer. So how many total breaths will a person take in her lifetime? 9 times 10 to the 8th, that is going to be 9 times 10 to the 8th. 1, 2, 3, 4, 5, 6, 7, 8. Put my commas so I can read this better. That is 900 million breaths in their life. Okay, and again, it was so much easier to work with the exponents than it would have been actually multiplying these numbers out, because we could do it in our head. All right, let's move on. All right, I believe this is our last practice one before we get into our closure and exit ticket. It says the Atlantic Ocean region contains approximately 2 times 10 to the 16th gallons of water. Lake Ontario has approximately this many gallons of water. This is 8 billion. How many Lake Ontarios will it take to fill the Atlantic Ocean in terms of gallons of water? So we're going to be having our ocean on top, and we're seeing how many times will this lake fit into it. So we're going to be dividing the ocean number of gallons divided by the lake number of gallons. Okay, so all right, starting with the ocean. The Atlantic Ocean contains about 2 times 10 to the 16th gallons of water. So I'm just going to write that here. And then we're going to do the lake, which is right here. This will become 8 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. Ninth. Okay. From there, I want you to go ahead and solve the remaining parts of this, and then we'll check it back in about a minute and a half. All right, let's check this. The first thing you should have done is divided 2 and 8. 2 divided by 8 is the same as 1/4, or 0.25 as a decimal. And then you should have divided these numbers. 16 take away 9 is 7. And then from there, we want to actually write this out as a number. So if we're doing 7 times, we're going to be moving this 7 times to the right. 1, 2, 3, 4, 5, 6, 7. And then our decimal point will go there, so it's 2, 5. 1, 2, 3, 4, 5, 6, 7. And that would be our final answer here. How many Lake Ontarios would it take to fill the whole Atlantic Ocean? It would take this many Lake Ontarios. To fill it up. All right, let's move into our closure and then our exit ticket. All right, our closure for today, just to summarize what we've done, we can compare very large and very small numbers by first writing them in scientific notation, then comparing them as a ratio. I don't know where it says ratio, and then simplifying our numbers using our knowledge of exponents, or those rules that we know. So maybe we have 80 times 10 to the fourth over 40 times 10 to the second. Well, 80 divided by 40 is 2. 10 to the fourth times 10 to the second, or divided by 10 to the second is 10 to the second. And then sometimes in our special cases, we can rewrite this out as an actual number. This would be 200. We can also do multiplication with our exponents. So maybe I have 5 times 10 to the second times 3 times 10 to the fifth. Well, I multiply my 5 and my 3. I would get 15. I would add my exponents because we have the same base. 2 plus 5, 7. Okay. And so this is how we use our exponents, or our scientific notation, and our exponent rules in real life situations. Let's go ahead and go over the exit ticket. Here's your exit ticket for today. It is broken down in Galileo into multiple choice questions, so don't freak out. You'll do this one little step at a time. It says most English-speaking countries use a short scale naming system in which a trillion is expressed as this number right here. Some other countries use the long scale naming system in which a trillion is expressed as this. Express each number as a single digit integer in terms of powers of 10. So the first thing you're going to do is write both in scientific notation. Okay. The second thing you're going to be asked to do is create a ratio. Third thing you're going to be asked to do is solve the ratio, so actually divide. And the fourth thing you're going to be asked to do is actually have your answer. So this question, how many times greater is the long scale than the short scale? Okay, again, this is multiple choice. It is in Galileo, and when you finish this in Galileo, please do your lesson reflection, as well as check off your checklist of your weekly responsibilities. Make sure your Moby Max is done for the week, and submit all of those things as well. Okay?